Let's talk now about how we can measure the mass balance of a glacier. There are two main categories, either on-site measurements or remote sensing measurements. Uh, the on-site measurement is tedious but very precise, or can be precise depending on the amount of effort you put into that. You can measure directly the snowfall and the surface melt by drilling stakes into the ice. It's labor and time intensive, but it provides pretty good measurements. So let's say you arrive at the beginning of summer before the ice really starts melting and you drill a stake into the ice. If you come back at the end of summer and you were in the ablation area, you might notice that the stake is sticking out more from the ice than what it was sticking out. Sorry, it's a complicated sentence. The stake is sticking out more at the end of the season than it was at the beginning of the season, meaning that that surface melted away. And that's how we can measure the ablation on the glacier. In terms of accumulation, we can, as I said, dig snow pits and get some density samples along a vertical profile. A more modern approach would be to fly a drone or a plane above a glacier and measure the ice surface elevation. You can do that by putting sometimes GPS on the glacier. Good luck to retrieve that GPS if something happens. But with planes, usually you can do what we call LiDAR measurements, where you have a laser in your plane that's sending a beam to the surface. The ice surface reflects that back to the plane, and you can measure the distance between the plane and the surface. And because you know the position of your plane, both horizontally and vertically, you know the altitude of your plane, you know the distance between the plane and the glacier surface. So ultimately, you know the altitude, the elevation of the glacier surface. We can do the same with the satellites. ISAT-2 is doing the exact same thing, sending a laser beam and then looking at the return of that laser and calculating the distance between the satellite and the surface that reflected the laser. Super accurate stuff, accurate to the centimeter. That's pretty nice. That's pretty cool considering that the satellite is hundreds of kilometers away from its target. The issue is it doesn't work when there are clouds. There are other techniques that I'm not necessarily detailing, but basically in Alaska, what we see is that nearly all the glaciers have been losing mass, are losing mass, and will continue to lose mass, especially in that century that's coming. And if we don't change climate right now, that is warming at an alarming rate. We have both direct measurements of surface elevation and snowfall on some of those glaciers, both from the field on site and from remote sensing. And those measurements show that the glaciers are losing elevation, they are losing mass. I just wanted to say a few words about sea ice because there might be a few questions about that in the exams, and I don't want you to mistake sea ice for glacier ice. Sea ice is not a glacier. I think I said that in the previous lecture, in lecture 1. Sea ice is formed by just the ocean freezing on the surface when it's cold enough. It's less dense than seawater, which is why the ice is floating on top of the water. But because it's salty, it's probably it is a bit more dense than glacier ice, if I'm not mistaken. It's never thicker than a few meters and usually melts during the summer. It wasn't always like that. Since, like 50 years ago, the sea ice was covering a much larger area on the planet, but it's shrinking by the year. We can have water inclusions in sea ice. So if you remember on glaciers, we have air inclusion into the ice. We have air bubbles. You can still have those in sea ice, but mostly those bubbles are filled with water. And the very interesting process is that as sea ice is being formed, the ice that the water that freezes kind of expels some of its salt into the underlying layer of water, meaning that beneath all of these islands of sea ice, there is super salty water that's laying just below. And this layer of super salty water is not super thick, but it kind of triggers a whole lot, many different processes that are super interesting. And so as water freezes, as the seawater freezes, it will create those bubbles that will have water in it and have much saltier water in those bubbles than the ice that's surrounding them. A bit of quiz preparation again. If the average amount of snowfall decreases over time, but temperature remains constant, what is likely to happen to the equilibrium line altitude? So snowfall that decreases, it means we make less ice, the input is going down, but the temperature remains constant. So the output remains the same. You still have a ratio of input-output, ice in, ice out, that is basically decreasing over time. So what happens if you melt more and more ice? The ELA increases. It's answer A. The ELA will go up if the temperature remains constant, but you create less ice because there's less snowfall on your glacier. Bonus style question. Ooh, that's a long one. You want to know the mass balance of a small glacier. You know that to do this, you need to measure the net accumulation and ablation using stakes placed in the ice. You install one stake at a high elevation, come back a year later, and measure a 1 meter increase in the surface elevation. You install another stake in the ablation area, come back 1 year later, and measure a 1 meter decrease in the surface elevation. Can you assume that this glacier is in equilibrium based on this information? And if not, what other information do you need to know? I'm going to let you think about that a bit. So don't hesitate to just pause the video for that. I'm going to give the answer. No, that's not enough information to say that the glacier is at equilibrium, because you can't conclude that with only 2 measurements on your glacier. You need to know a bit more about that. You need to do more measurements on a larger area. And eventually you will have enough measurements that you can kind of average the amount of ablation for the entire ablation area and measure the average accumulation for the entire accumulation area. And if you conclude that, if you see that you have a meter of accumulation in the accumulation area, a meter of ablation in the ablation area, and that those 2 areas are equal in size, then it means that the glacier is at equilibrium. You could also look at if the glacier is advancing or retreating, even though that's not, you can have a glacier that retreats and still builds a lot of ice. You can have a glacier that stagnates and is melting a lot, but if you measure the ablation for the entire ablation area and accumulation for the entire accumulation area, then you will have a good idea about if the glacier is at equilibrium or not. So to summarize quickly, we saw that snow undergoes a densification process, metamorphism, and turns into fern once it survives summer, and eventually becomes ice once all of the air bubbles, when all the air is trapped into the ice and cannot escape the material. So density, very important, is equal to mass and volume. The net mass balance of a glacier is the difference between the accumulation and the ablation. And if a glacier is gaining ice mass, a glacier is gaining ice mass if more snow accumulates than ice melts away, and vice versa. And finally, the ELA occurs at the transition between the accumulation area at high elevation and the ablation area at low elevation. You never have ablation area that's above the accumulation area. It just doesn't make any sense, because as you go higher on the glacier and in altitude, it becomes colder, and therefore you increase the probability of having the snow survive your summers. So that's it for this lecture. I think, yep, that was the last slide. So I'll see you later for the 3rd lecture. Have a nice day, evening, whatever. Bye-bye.